fingerprinting LLMs via prompt injection.
This paper addresses model provenance by using prompt injection. It reports high true positive rates and near zero false positive rates. We will examine the problem, the method, its performance, its limitations, and the main takeaways.
First, let's define the problem. The goal is to verify if a suspect model is derived from a base model. This is difficult because post-processing techniques like fine-tuning or quantization can alter the suspect model, obscuring its origin.
Existing methods are either proactive or passive. Proactive methods embed signals during training, but this modifies the base model and cannot be applied to models that are already released. Passive methods analyze a model's inherent behaviors, but these behaviors may not be unique or robust enough for reliable detection.
What are the assumptions about access to the suspect model? The paper defines 3 access levels. White box is full access to parameters. Black box is access only to the final text output. The paper also focuses on the gray box scenario, where an investigator has access to token-level probabilities, which is a common setup for commercial APIs.
The core idea here is to use prompt injection, which is normally an attack vector, as a defensive tool for creating a fingerprint.
Correct. The method creates what it calls fingerprint prompts. These are optimized inputs that force the model to make a choice between 2 specific tokens. The prompts are designed to be near the model's decision boundary for that token pair, making the model's output a sensitive and unique signal of its identity.
How is this implemented?
There are 2 stages. The first is fingerprint construction, where the prompts are optimized for the base model. The second is fingerprint verification, where these prompts are used to test if a suspect model exhibits the same token preferences.
Construction is an optimization process. It uses a uniqueness loss term, LU, to ensure the prompt places the logit difference between the 2 target tokens near 0. This positions the prompt at the decision boundary, making the behavior discriminative.
There is also a robustness loss term, LR. This term maximizes the logit difference between the target tokens and all other tokens in the vocabulary. This makes the fingerprint more stable against modifications like quantization. And how does the verification stage work? For a set of fingerprint prompts, a reference bit string is generated from the base model's token preferences. A predicted bit string is then generated from the suspect model. The bitwise accuracy between these 2 strings is computed and compared against a pre-calibrated statistical threshold to make a determination.
Let's look at the evaluation. The method was tested on 5 base models and approximately 700 derivative models. What were the results?
In both gray box and black box settings, the method achieved high true positive rates, or TPRs, generally above 0.90. The false positive rates, or FPRs, were near 0 across all tested base models.
How does this performance compare to other passive detection methods? It reports higher TPRs and lower FPRs than the baselines it was tested against. For example, for post-trained models in a black box setting, its TPR was 0.944. The paper notes that other methods like TRAP and LLM map can suffer from high false positive rates in the same scenarios.
What about failure cases? When does the detection fail?
The paper's analysis suggests that failures, specifically false negatives, occur when the suspect model's behavior has substantially diverged from the base model. The misdetected models showed degraded performance on standard benchmarks, indicating the issue was with the integrity of the suspect model itself, not the fingerprint. Is performance affected by practical API limitations, such as only getting access to a limited number of top token probabilities? The authors tested this by restricting gray box access to only the top 20 probabilities. The detection performance for post-trained models was identical, and for quantized models it was similar. The false positive rate remained 0. Could the method be defeated by a system designed to detect prompt injections? The fingerprint prompts were tested against 2 existing prompt injection detectors. The prompts achieved bypass rates of 0.95 and 0.870, while detection performance remained high.
To summarize, what are the primary contributions?
The paper presents 3 contributions. First, the method of constructing fingerprints via prompt injection. Second, a unified verification framework for gray box and black box access. And third, an evaluation across nearly 700 models that shows improved performance over the selected prior methods.
This leaves us with several takeaways. First, consider using inherent vulnerabilities for defensive goals. Second, framing complex behaviors as simpler classification tasks can reveal unique signals. Third, use statistical methods to calibrate detection thresholds. Fourth,
Test robustness against realistic constraints. And finally, correlate detection failures with the potential degradation of the asset being tested.